using every tool in their armory in order to increase extraction efficiency and sustainability. Advanced products are increasingly being used, such as high-strength steels, light and rare metals, for more demanding duties in the field. And of course, economic growth continues to drive demand, particularly in China, albeit at a reduced growth rate that we've seen in recent decades. But they continue to drive demand for construction and mobility. So let's look at a typical steel production workflow. And what we want to explain here is how microscopy is able to provide solutions to various problems, various requirements within the steel value chain at the steel mill. So firstly, the natural resources themselves. Microscopy is able to perform a critical role in analysing the mineralogy and the composition of the coking coal. Through the successive furnaces into secondary steel making, where the continuous casting is a particular hotspot for microscopic analysis, such as standardized non-metallic inclusion analysis, which, as I'll explain in detail, is critical in the quality and performance of the finished steel, as well as the analysis of semi-finished and finished products. So as I've said, the mineralogical and maceral composition, that is the coke and coal composition of both ore, coal, coke and sinter, as well as the slag produced from the blast furnace and the electric arc and ladle furnaces, for beneficiation and for maximum value extraction. Spectroscopy, of course, can be used for both near-line and offline chemical monitoring. And then a classic microscopy application is the routine norm-based QA and QC of non-metallic inclusions. That can be taken a step further with advanced near-line and offline inclusion measurement and characterization with techniques such as EDS and EBSD within the electron microscope. And of course, advanced characterization of grains for the most demanding duties, and this is really in high-level research applications. So what we want to show is that really analytical microscopy is able to offer a one-stop analytical solution, which is able to perform many roles within the metals value chain. So through the application of different accessories and different techniques, we're able to obtain a flexible, seamless integration of many accessories for many experiments in research and routine analysis also. I'll go into particular crystallography and spectrometry and assays, particle analysis, including size distribution. Mineralogy is also a topic which has a huge potential to improve the efficiency of the steel plant, as well as tomography measurement, petrology, and conventional imaging, that is to say, metallography. This slide shows how we can correlate materials analyses over different length scales. So the structure, chemistry, mechanisms, and microstructure is able to explain and determine the performance of the steel itself. So from a surface inspection point of view, microscopy, either through optical or electron microscopy, is able to perform failure inspection and crack analysis. And that's in the macro range as well as the micro range. Down into the millimeter range, you're able to measure inclusions and 3D voids within both LM and EM as well as XRM, X-ray microscopy. In the submicron range, particle chemistry is a critical application of microscopy in the analysis of inclusions and the chemistry of imperfections. And non-destructive tomography as well, which is an XRM application, and that can be done in the submicron range, which is an additional complementary technique to EBSD, which we'll discuss shortly. And then in the nanometer range, you have crystallography through EBSD, which we'll explain the power of shortly, as well as nanotomography. And this is the FIB-SEM, the focused ion beam SEM application, including milling on the nano scale. So they're the techniques, and you can also add, which I'll briefly touch on, Raman spectroscopy, which is able to add not just elemental analysis, but an oxidation state analysis in the chemical analysis of inclusions and corrosion products, for example. So I want to explain the true potential of light microscopy in the steel industry, and although light microscopy is well disseminated for standard analyses, it really does have an extreme power and a huge number of outputs and analyses and uses within the steel value chain. So why optical microscopy? So this really splits into two areas. So it's the production parameters within the steel plant for monitoring and quality control, as well as the understanding the properties in metals research and quality assurance, or in this case, in failure analysis and understanding exactly why a failure may have propagated. So there's an extensive range of quantitative image analysis techniques and actionable information that can be gained purely by inspecting through a light microscope and using some of the advanced analytical techniques that the modern microscope can offer. So, as we can see, a typical range of informations from the LM include grain size and area fractions of the multi-phases within a structure, textural parameters and topography, and you can also measure texture in down even to the nanometer level using LM, using different techniques. Non-metallic inclusions, as I say, the classic example within light microscopy, as well as layer thickness and porosity within a sample. So how do you use that information? We call it actionable information. Well, what actions can be taken? Well, those parameters will determine the structural and performance of the metals themselves in terms of their hardness, their tensile strength, ductility or brittleness, purity, all determined by the alloy composition, the inclusion composition, and then to sort of close that loop, then fatigue analysis and prevention. And when a failure such as this aircraft window does occur, then to find out exactly the failure analysis in order to understand that failure. On the production side, the use of microscopy can then be used for optimization of the parameters within the steel mill. So the heat treatments that are required, the plastic deformation that is present within a steel, the recrystallization and annealing that is required upon a certain piece of steel, the furnace parameters and the rolling parameters within the mill, and when a single batch of steel is continuously cast, then it may be perhaps even a week from the start to the end of a batch. It's critical to understand in real time or close to real time the evolution of the microstructure of that steel and therefore its performance. So let's see how that translates into the recrystallization and the treatment parameters. Well, clearly, tensile strength and ductility are very closely proportionate to the grain size within the steel billet itself. So the cold work grains, which might have been freshly rolled, are then heat treated or annealed, and clearly you see the growth in the grain size. So after the cold working of a metal, by rolling, dislocations are created, and that imparts mechanical strength but also brittleness. So you can see that the tensile strength will increase with annealing, but ductility will decrease. Recrystallization then allows grain growth, and that creates a highly ductile steel. Typically, structural metals are polycrystalline, and the crystal structure can be revealed and analysed and measured, but it does require mechanical preparation, so that'll be cutting, grinding, polishing, and also etching if required, and I'll discuss that on the next slide. So microscopy and grain size measurement within microscopy is a critical tool in quality control. There is a direct relationship between the grain size and the two of the most critical parameters in a structural steel. This is standardized. The ISO 643 standard is used for grain size measurement. And there are different methods to do this. There are what's called an intercept method of measuring the grains in a single line, a comparison method, which is very fast, but it's manual, which uses comparison charts. But even better, there is automated grain measurement, and the modern light microscope is able to perform a huge variety of analyses and measurements automatically. Just as an aside, that does require good sample preparation, and this mustn't be ignored. So in this case, this was some work done at Witwatersrand in South Africa of a platinum aluminium alloy, both in the unetched state. This image has been taken on the left with an SEM, and also after etching and imaged with a light microscope. So etching and the cutting, grinding and polishing stages are critical in revealing this microstructure within the alloys for inspection through microscopy. So in this case, these platinum alloys were electrolytically etched in a solution of hydrochloric acid with sodium chloride using a direct current. And that etching enhances the microstructural images of these platinum aluminum-based alloys. So here, this is an electrolytic etching process, Barker's process, to enhance the grain contrast. And then the whole reason for doing this is to reveal quite clearly this grain structure for both manual or automated grain measurement. I will stress that these two are not false color images. These are reflected light images of an aluminium sample after etching, imaged using different polarization contrast modes, firstly without and then secondly with a lander plate. But the interference patterns can also provide topographical info. So a differential interference contrast mode can be used in polarized light, and that actually enhances the edges, even if they're a few nanometers high, by splitting the beam into slightly offset images. And then the user qualitatively is able to inspect in better accuracy, better precision, where this sort of very subtle ridge or change in height might be visible, which wouldn't otherwise be visible necessarily on the light micrograph. What this does require is rotating the stage to maintain the polarity and create the image. As an alternative, there's a circular DIC which uses circular polarized light rather than linear polarized light, which means that the polarization needs only to be rotated, so the sample does not, and the stage does not need to be. So it's a quicker throughput, more information, and it can produce some really stunning images. So next, I want to talk about why inclusion analysis in steel. So this is a recognizable schematic of a rolling mill. So the original grains are rolled and deformed and elongated, and it's at this point that any inclusions in the steel at this point will themselves become deformed in the same orientation as the grains themselves. During recrystallization and heat treatment, that is, new grains will then form, and until the recrystallization is complete. But those inclusions will remain in that steel, and they will. And once the steel is cooled, then they will influence the mechanical properties of that sample. So, for example, this is a typical mixed inclusion, likely to be a sulfide and oxide inclusion, slightly elongated. You can also image this very beautifully with an in-lens backscattered electron detector, and this is the result of such an inclusion, which is a fracture. This is a fracture surface in an aluminium sample, and the likelihood is that this crack has propagated from an inclusion or a piece of porosity. And in the real world, this is an image from actually the Ministry of Defence in the UK. This is a piece of work done in the late 1950s on a de Havilland Comet aircraft, and a crash of that aircraft was responsible for a lot of the pioneering work on metal fatigue in real-world applications and in the aviation sector. So there are real opportunities, real applications of this information and this data. So the inclusion, once you measured the inclusions, then that will determine the grade of the steel. So non-metallic inclusions, they're typically oxides, sulfides, and nitrides, and their distribution will have a considerable effect on the properties of the steel. So inclusions always form in the rolling orientation for fairly obvious reasons. Soft inclusions will create lines, and hard ones will more fragment into stringers, which are fragments of the original inclusion which are broken up in the rolling orientation. You're able to do some qualitative analysis of these surfaces. So you're able to identify. So bright grey will typically indicate a soft sulfide, but black dots in or outside stringers indicate that there are hard oxide inclusions. Graphite analysis is also possible within specific modes within a typical analytical light microscope as well. So you're able, even with a light microscope, to provide some qualitative information at least about the chemistry, and quantitative information about the grade applicable to the batch of steel according to the number of inclusions. So automated image solutions on the market offer reproducible and auditable results in accordance to current standards, particularly EN 10247. But as I said before, that it's fast and inexpensive to do manual methods and involving comparison charts, and they are still in use because they're easy, fast, and relatively repeatable still. So this is an image of a mixed inclusion again. So you can see the light grey sulfide and the darker grey oxides. But you'd really have to look in the SEM to analyse these in full for the elemental analysis. So cast irons are a class of ferrous alloys with carbon and silicon as major alloying elements. Good castability and machinability and moderate mechanical properties, and so they're used for many applications in various industries due to the economics of these materials. This, for example, is an engine component. The cast iron has to be analysed due to the morphology of graphite, which has got a huge influence on the mechanical properties of cast iron. So metallographic quality control of grey iron is an integral part of the production process. So the morphology, size, and distribution of the graphite is determined on an unetched polished sample, and to check the structure of the matrix, the sample is etched. So the results can be compared with standard reference comparison charts, but also in the modern digital microscope, various high-quality image analysis techniques are available to do this automatically and with an unprecedented degree of precision. We showed this slide before. This is the automatic detection, measurement, and reporting. In this case, of a sulfide inclusion. So such inclusions disrupt the homogeneity of the structure and influence the mechanical and other properties. So finding the balance between good machinability for cost-effective production and the right mechanical properties is the goal for quality assurance with NMI. So the standard test method is a microscope equipped with a very specialized software module. I hope you can see this quite clearly, but the software will automatically scan and identify each inclusion. It will then create a gallery of those inclusions, create a table of their measurements and diameter, and rank those inclusions, and then produce a report which can be used in the certification of the grade of the steel. And if we going back a couple of slides, then the inclusion area has a direct effect on the use and the specialized use to which they can be used. So for a very high inclusion, then rebar within concrete is acceptable. But clearly the higher value alloys will be the more specialized and lower inclusion applications. So this is just an example of where the vermicular graphite has been used for automated nodularity measurements, and the surface area is being automatically computed to assess by the light microscope to assess the criticality of those inclusions. One completely different part of the value chain in the steel mill is vitrinite reflectance. So this is where the coking coal, or the coal itself, can be analysed for the macerals, and that is the maturity and the reactiveness of the particles within the coal. Now, of course, the blast furnace is not a smelting operation; it's a reaction between coal and iron ore. So the categorization of the coal and coke, as well as the iron ore, needs to be done according to rank, which is the maturity of that coal, and that's done by measuring the light reflectance of the vitrinite macerals, as well as the type. So that's done with point counting to obtain the volume percent of the coal macerals. And in doing so, even a very small improvement in the understanding of the composition of the coal and the iron ore, you can increase the yield from your process, from the primary yield from the blast furnace, with the commensurate increases in yield and efficiency. So petrography is also used to determine the amount of contaminants, such as quartz and pyrite, or the amount of oxidation. These are also done to various standards for both ISO 9404 and 0.3 and 0.5 to perform those light microscopic classification of coal. And this is a semi-automatic process, so a volume percent concentration is determined for a minimum of 500 observations, and in practice the user will typically perform a manual calibration step whereby the instrument will present to the user 1, 2, 3, 4, 500 points, and then the user will segment manually into the different phases, that is vitrinite, semi-fusinite and inertinite typically. And then the instrument can then, once calibrated for that sample, it can then analyze thousands of points automatically. Just one last touching on light microscopy. So in additive manufacturing, the powder metallurgy is critical, and there are a number of insertion points for microscopy within the powder manufacturing, powder sintering, and laser melting regimes, and also the quality inspection of the finished parts. So powder metallurgy is used for near net shape manufacturing. It can be, but is not necessarily porosity free. And the quality of the finished part depends on the particle size distribution and sphericality of the powders themselves. And with a modern light microscope, you're able to perform this analysis completely automatically to do the particle size distribution, and you can calculate the weight percent. Here, a light microscope and an SEM has been used to image the powder particles. And then this is a drill bit, which has got helical cooling channels. And then this has been analysed or checked for quality in section by a smart zoom digital microscope, as well as the surface being inspected both for the laser tracks and porosity and the bulk microstructure. And this is an etched sample of a cross section. And this is what we're talking about. This is a roughly 20 micron ferrocerium particle, which has been imaged with field emission SEM. So now we'll talk about electron microscopy and what we call correlative multimodal microscopy. This means that it's a quantitative single solution nano laboratory, or a laboratory on a nano scale. So let's familiarise ourselves, or refamiliarise and recap the different imaging and analytical modes. We talked in quite some detail about EDS or EDX, energy dispersive X-ray spectroscopy, as well as WDS and some touching on EBSD. But we will go into some more detail in 3D in the following slides. You can also integrate Raman spectroscopy, which opens up new opportunities in analysing not so much the metals themselves, but more the oxidation and corrosion products of the metals themselves, as well as the chemical analysis, not just an elemental analysis of the inclusions themselves. And of course, as we said before, the optical imaging and X-ray imaging can also be used to correlate either the LM with the SEM, or indeed the XRM to the SEM, which is the highest resolution. This is an image from a Gemini SEM, which is another field emission system, and you can see the dislocation networks in a highly deformed stainless steel. And the different imaging modes make this sort of clarity of understanding of the deformations within the metal possible, which would not be visible on a light microscope. So the electron beam to sample interaction in an SEM creating these image modes include the primary electron beam will penetrate the sample a different amount depending on the power of the beam itself. Secondary electrons are then emitted from the sample, and that's the key imaging mode, the standard imaging mode through an Everhart-Thornley detector within an SEM. Backscattered electrons can also be detected in a different plane away from the sample. Emitted X-rays from electronic transitions within the sample are able to describe the elemental analysis, the elemental composition of the particular point sample being analysed through EDS as well as wavelength dispersive spectroscopy, which is a much slower but much higher resolution kind of mode. And the diffraction of the electrons creates an opportunity to perform crystallography in situ on your bulk sample within the SEM. Finally, the cathodoluminescence detector is able to analyse emitted visible light, which provides more information about the texture, and particularly in geological samples. So let's sort of recap again, so to remember the advanced EDS, and we'll go into three-dimensional EDS. So this, for example, is from Oxford Instruments. This shows the elemental mapping of a particular inclusion or a particular phase or particular impurity within a piece of steel. And by segregating the data from different wavelengths of emitted X-rays, you're able to assess that this inclusion is chiefly a chromium inclusion, but you're also, from these bright spots, able to determine the location of iron within those inclusions. You can also see these rather dendritic growths, which are high in magnesium within that sample. So it's a very powerful local elemental analysis technique. And this is an example which we showed in the previous webinar, whereby an inclusion. This is through tunneling emission microscopy, STEM, where the chromium-rich phase has been analysed by tuning the EDS. So you can see that this inclusion has been shown. This is a chromium map, and this is an iron map. So the concentration of chromium corresponds to the bulk of the iron. Just as a little aside, so as an advanced insertion point, if you like, for EDS within the value chain, so the ore analysis within sinter production within the steel plant is a use for automated mineralogy. So this is the automated segmentation, depending on size and chemistry, of each of these species within a bulk ore. So you're able very accurately to determine the different mineral species, and that could include the local assay, the local species, the local the mixture of minerals within that sample quantitatively. So for a typical iron ore sample such as this, you're able to find the elemental distribution, the total elemental distribution, therefore, i.e. the total composition of that particular sample, and also the mineral locking characteristics. So then you may need to tune your process of sinter manufacturing, sinter production, or the blast furnace itself, according to the mineral associations, textures, and chemistry and phases within the SEM. And this can actually be done, and this is an example at a mine site. This can actually be done sort of in a very mobile, ruggedized systems which are available. Let's talk now about FIBSEM, focused ion beams. So this schematic shows how this works. So within the SEM, you have the primary imaging beam, electron beam, which can perform the EDS map of a certain face, a certain plane. What then occurs is that an ion beam, typically gallium, will move back, quickly mill back the sample in the Z plane, which means that successive EDS maps can be performed on different slices of this sample. The reconstruction of that grain structure is able to map in 3D the elemental composition through EDS, and you can also perform 3D EBSD for the 3D crystallography and grain structure of that sample. Actually, the most common, this is a sample of it's a TEM lamella. So actually one of the principal uses for this 3D sectioning technique is the preparation of TEM lamellae. So this, you can see, this is roughly a 15 micron coupon for use in the TEM, and actually the use of a FibSem is one of the critical factors in the imaging through TEM. So to go back to this 3D EDS idea, this is a different sample of a metal sample. So combining the SEM with a cross beam, a second beam, as I said, the cross beam, there are other equivalent microscopes. EDS is then a fully three-dimensional analytical technique. So the focused gallium, or it can be a gold or iridium beam, is used to section the sample, and then the EDS map is collected after each slice removal. As I said, it's particularly useful for analysing defects, but particularly for preparing precise TEM lamellae in very high definition. 3D EBSD is also possible, which I'll speak of shortly. And to give you an idea, roughly a 24-hour period is able to image in 3D roughly a 100 micron cube. So the reconstructions that you can do here, in the same way that you can do elemental mapping in 2D, this is the 3D SE image, but you're also, in this case, so silver, tin, indium, you're able to do that mapping in 3D and understand the structure and the chemistry of inclusions and the grain structure of the steel itself. The nanomachining side, well, you see, you typically see these little X's, which are calibration points for the instrument, and an array of TEM lamellae. This is in silver, nickel, copper alloy. Would be prepared, and typically per sample, this kind of 20 micron area can be milled within about 18 minutes. So it is a relatively fast technique. So just to finish on FibSem, this is an example of a 3D reconstruction of a cracked steel sheet. So what has been done is the crack has been located either by eye or within the light microscope, and then the FibSem has been used to mill, image in 3D the anatomy of that particular crack. And combining this purely imaging example, you would then be able to do 3D EBSD to understand exactly the chemistry of the inclusion or the shape of the crack from which that failure occurred. So EBSD, let's go into some more detail about EBSD. It's a form of crystallography. The diffracted electrons can study any crystalline or polycrystalline material, and it involves the understanding the crystal orientation and phase of the materials in microstructures, but it can also reveal texture defects and deformation. So just to reiterate the operating principle of EBSD, so the EBSD detector will be installed adjacent to the EDS detector. So the scattered electrons, and you can see the very specific orientation in which the sample is held. An EBSD pattern is created on the detector. Bands are detected, deconvoluted, and identified, and from that the crystal orientation can be determined and compared to libraries to assess the identity and the composition and the grain structure. The species present. Again, this is a reiteration, but the critical thing here is the orientation maps. So adjacent grains will be in different orientations, and the crystal orientation will display in this case in a different color. Pardon me, in a different color. And alongside pole figures and inverted pole figures, you're able to identify within a single grain where that grain structure is strained. And that's very important in predicting and analysing failures and potential failures. So the latest thing in high-speed EBSD, and I'd like to thank Oxford Instruments for these images and data. The new symmetry detector, for example, is able to. This sample here on the right, top right, is a duplex stainless steel. So you can see the blue is ferrite and the red austenite in a weld. So roughly, this image is being collected with roughly 50 million points at 2,000 points per second. So that's roughly 7 hours for this. As you can see, it's a several millimeter cubed sample. So this, to zoom in, then you can see the true resolution of the map and the actual resolution. But the critical thing is that both EDS and EBSD can now be collected in real time to index and visualize data at roughly 3,000 frames per second. Metal's a particular sweet spot for this application, and for high-speed EBSD, as you can acquire accurate data particularly quickly on metallic alloys and underformed metals. But it's also suitable for oxides and thin films. So as we covered in the last talk, you can also have in-situ heating and tensile stages, which are available for a range of SEMs. And high-speed EDS and EBSD can therefore track these experiments of strain and defects and grains in real time. So this is an example that we showed in our last webinar, whereby the deformation of the grains, pardon me, is visualized through a gradient in the color of the display. We also covered the austenization and annealing of ferritic and austenitic stainless steel. So you can see that this 3BSD, you're able to analyze determine the annealing temperature required for a ferritic stainless steel to an austenitic stainless steel. And then in this case, the temperature has been cooled gradually to transform back into a ferrite. You can also identify the grain crystallization, so the orientation maps of the particular ferritic and austenitic species and back to ferritic species, and then you can measure the grain parameters of that sample before and after annealing. So 3D EBSD extends EBSD into FibSem in 3D, completely automated, and as I said, roughly 12 to 24 hours to image a 100 micron cube. So you can see that successive slices are imaged and then built up into an array, and then the software is then able to reconstruct and analyze the grains in 3D. An extension of this is transmission Kikuchi diffraction, TKD. This was developed by NIST in the last 5 or 10 years, and it's essentially a transmission EBSD. So the Kikuchi scattering that is measured is responsible for, pardon me, which is responsible for diffraction occurs within a few nanometers of the exit surface of the specimen. So what this means is that there are higher spatial resolutions, which can be better than 5 nanometers, whereas EBSD on a bulk is limited to roughly 25 nanometers spatial resolution. So this is particularly important with nanostructured materials, which may require higher resolution. Completely conventional FE-SEM and EBSD hardware, but the samples themselves are thin electron transparent, such as TEM lamellae, in a special holder. So this is the conventional EDS detector. You can see the angle of the scattered light, and this is what it looks like in situ. Just one quick slide on Raman spectroscopy. As some of you may know, the Raman is a non-destructive spectroscopy, vibrational rotational spectroscopy method. It can now be used in situ within the SEM, whereby the laser light can be focused on the sample, scattered light is detected, and depending on the vibrations in chemical bonds, that scattered light is shifted in frequency. So Raman's shift is referenced to known databases to identify specific chemical components. And what this does is complement EDS analysis in that you're able to add oxidation state analysis and use this for stoichiometry, also stress and strain, crystal symmetry, orientation, and doping and crystallinity. So differentiation between the metals themselves elementally must be done by EDS, but then differentiation of the oxides is occasionally possible with EDS, but Raman spectroscopy can easily identify various oxidation states. So although it's not a critical metals technique, it can provide specific information about oxidation states of corrosion products, differentiate inclusions, contaminants, and in the automotive industry, for example, then organic and inorganic fibers. So this is a Raman overlay on a geological sample, courtesy of VTech, and you can see that the the Raman spectrographs have been mapped in different colours, and this is a typical Raman spectrum of a mild steel corrosion product. So you can see magnetite, hematite, goethite. So what this means is that you can differentiate those oxidation products in the SEM with an oxidation state analysis through Raman. So our final section is about X-ray microscopy and diffraction contrast tomography. So, reiterating the work that we presented in the last webinar, an X-ray microscope uses X-ray radiation for imaging rather than visible light or electrons. And the key benefit here is that X-ray penetration of most objects means that a huge variety of materials, both natural resources, metals, and and biological samples can be imaged in 3D non-destructively. This, for example, is a 3D printed part, a couple of millimeters or so, and you can image in the solid domain to show where the packing density is imperfect. So you can see where there is porosity within 3D printed part and unsintered metal powder particles. And then, interestingly, you can then image that in 3D in the pore domain to better understand, calculate, and visualize the 3D structure of the printed part itself. So here is this is diffraction contrast tomography. So previously, DCT has only been possible with a synchrotron, but it's now possible in the laboratory with a microscope such as the X-Radia Versa. It uses a white or polychromatic divergent X-ray beam and specialized apertures and beam stops, and a dedicated detector are able to perform the analysis of the scattering of X-rays from the sample itself. The sample is critically equidistant between the source and the detector, which allows the algorithms to identify precisely the crystallography and diffraction patterns. And the sample itself is rotated while being moved through that beam in order to generate an image in 3 dimensions. So this is an example of a beta 21S titanium alloy. So you can see that an EBSD-like crystallographic map has been determined in 3D, and although there is no chemical information there, you're able to identify the crystal structure within that sample. A tessellation, incidentally, is a basic space-filling algorithm using the input from the lab DCT reconstruction, and furthermore, in future, more accurate grain morphology algorithms will be developed as the technique progresses, and with successive generations of the technology that is occurring. In steel, here's our schematic again. So you can do this non-destructively within a steel sample. So whereby you'd be able to perform light microscopy of annealed samples at 500, 600, 700 degrees of those recrystallized samples. It's a destructive technique, and it's an offline technique, whereby you could put the same coupon within the DCT system, perform the heating experiment in situ, and as a result be able to view in real time in 4D the recrystallization effects of that steel. So you can see that the grain diameters have varied depending on the temperature, and that's what we can visualize in the light microscope, but we can quantify it in the X-ray microscope. Where the XRM is particularly interesting is in correlative tomography. So we talked about FibSEM and the 3D analysis through EDS and EBSD. The power of X-ray tomography is that, so for this roughly, 1 millimeter cube sample, you can actually target in 3D exactly where you want to mill using the FibSEM. So non-destructively, you're able to perform a micron scale image analysis of inclusions and voids in 3 dimensions, quantify the size and shape distribution, and then only target the nanoscale precipitates and grain structure you want specifically to analyze using the FibSEM. So this has got a huge benefit in the time to result, in the selection and judicious selection of the area that you want to mill through the FIB-SEM. So it's a very high throughput technique as well. So compared to 3D EBSD, here you can routinely acquire grain statistics on larger volumes at faster acquisition times. So whereby the sample image with EBSD, so roughly 100 micron cube, would take 12 to 24 hours and destroy the sample. With lab DCT, you can non-destructively image in 12 hours a 2 millimeter by 2 by 2 cube and reconstruct and perform the 3D grain map of the entire volume. So in terms of productivity, it's approximately 11 years to generate the same volume imaging and analysis in 3D compared to this 12 hours within lab DCT. So it's a very powerful technique. Just before we finish, quickly, the stress corrosion cracking in a steel. So the extent and shape of cracks within samples help researchers understand how damage initiated and has evolved. But observing cracks in 3D can be very challenging. So classical 2D technique, such as this like micrograph, may assess 3 or maybe even 4 or 5 specific different cracks. And if you do want to verify that information in 3D, you'd require cutting open the sample, but that's dangerous because you can possibly create new cracks or change the geometry of the existing crack in the process. XRM presents a nice solution because we can look at the interior crack geometries without cutting the sample open. And then the software is able to isolate in 3D, produce a model of that specific crack. And in this case, you can see that the surface appears to have maybe 3 cracks, but actually beneath the surface, they coalesce into a single large crack. So it vastly increases your ability to rapidly understand a crack non-destructively. Final example on the X-ray Versa. So this is cracking damage in wet welded joints. So this is particularly useful in an undersea environment. So hydrogen is relatively available in underwater wet welds due to dissociation of water at high temperatures. But that leads to low weld toughness and thermal contraction during the cooling, which nucleates cracks. That can seriously affect the mechanical properties of the weld. So in this case, X-ray microtomography and image analysis are employed to image and measure crack length and morphology in the weld metal of a wet welded low carbon steel joint. The images were corrected and the cracks were segmented and post-processed to correct for artifacts, for example. And then the size and shape parameters were measured to show a large average value for the ferrite diameter, which is the largest particle diameter, compared to the crack thickness. And 3D renderings of the detected cracks reveals a spatial distribution in which densely cracked regions are separated by regions of crack-free material. So just to sum up very quickly, because we're running out of time. So microscopy really, a full correlated microscopy portfolio is able to provide a full analytical solution for a large variety of multimodal, multi-scale research challenges, both in research and in production. So analytical microscopy and metals analysis is able to supplant a large variety of different techniques. We've talked about 3D tomography, crystallography, assay and spectroscopy, and particle measurements, mineralogy and ore grading. So you can integrate multiple accessories for various experiments in both routine analysis in the steel plant and in research itself. So how does microscopy enable resource efficiency? Well, there's unprecedented understanding of process inputs for maximum resource recovery in a competitive world. Faster time to more accurate results which wouldn't otherwise be visible in nearline QA and QC. An analytical power in a single instrument or a single solution to microengineer structural alloys, printed metals and light metals. And microscopy offers a vast array and depth of connectable physical and chemical data. So whereas metallurgists have long understood that microscopy is their eyesight into the micro and the nano world, analytical microscopy is now able to be used to perform a vast array of experiments, previously requiring an extensive, generously equipped analytical laboratory and wet chemistry as well. So we're now able to perform many of those jobs in characterizing physical and chemical processes automatically and in real time. So I'd like to say thank you very much for your time and your attention today. I'd like to hand back to Kelly and ask for any questions that you've submitted.
Okay, thanks, Andy, for the great presentation.